Welcome back to module 7. We are discussing non-adiabatic transition, non-radiative transition. They are synonymous, but we haven't discussed this non-adiabatic coupling yet. We will do that in a later stage. We are using non-adiabatic coupling, the concept of non-adiabatic coupling, which is involved in non-radiative transition. And we have said that it is constant, it does not depend on time. That is why, but this is coupling two states which will undergo the non-radiative transition. So, what we have seen so far is that this part is a time independent part, and that is why it can be taken out of the integration. So, I can write it down directly like this way. This Cm part I will write down like this way. Cm T1 is nothing but minus I by h cut, then this spatial integration part, this element, and it will be taken out. It has been taken out of the integration because integration is over the time, and this is omega, this is e to the power I omega mn t then dt. So, if we integrate this one, what I get is here is I by h cut, then this integration part, and then e to the power I omega mn t divided by I omega mn 0 to t1 time. 0 to t1 time is the t1 time is the end time for the interaction. Immediately after the interaction, we are trying to find out what is the Cm, because from Cm I will be able to get the population at the mth state, the final state. So, but this one I can write down as I by h cut, then h mn, then e to the power I omega mn t1 minus 1 divided by I omega mn, if I use the limits. And little bit trick we will make here to get a convenient form of this expression. I by h cut, what I will write down here is I by h cut, then h mn dash, then t1 by 2, I multiplied by t1 by 2, and e to the power I omega mn t1 by 2. If we do that, then within this bracket I will be able to write down e to the power I omega mn t1 by 2 minus e to the power minus I omega mn t1 by 2 divided by I omega mn t1 by 2. So, what we see here is that this part can be written as the 2I sine omega mn t1 by 2. So, I will erase this part and we will just write down 2I sine omega mn t1 by 2. So, as a result, finally what I get here from here is that we can simplify it further, and we can write down this is nothing but minus I by h cut h mn dash t1 e to the power I omega mn t1 divided by 2 multiplied by cardinal sine function of omega mn T1 by 2. That is the final form of CMT1 we get. And once we get this cardinal sine function is nothing but it is a sine x by x. So that's exactly what we have. This is sine part here, and then the another part, this x part is here. So cardinal sine function we are using to express this population. So finally, we have to consider the square magnitude, the square of the absolute value of the Cm, and we take the square of it, and if we take the square of it, finally we get this expression for the population at the mth state. So we started with n state, discrete state, and interaction was on for t1 time, and we are trying to find out what is the population at the final state. So the population at the final state immediately after time t1, when the process of interaction between two states switched off, represents the probability of transition from initial state to the final state. So probability of transition is nothing but how much population in the final state, because the probability of being in state m is the probability of transition from state n to state m due to the constant perturbation. This part is not time dependent, this is time independent. Therefore, the probability of transition from initial state to the final state is given by this, and if you look at this cardinal sine function, this function is actually is a very sharp function. It exhibits a very sharp peak with a width, and here width, when I say width, I will not use this full width half max. Generally we use this full width half max, but I will say when the function becomes 0. So this is the width we are saying, and this width would be when this Em minus En T1 divided by 2 h cut, when this becomes pi, then the function value becomes 0, and we are defining this is to be the width. So if we have, and then later there are some oscillation, but these are very low magnitude, there is almost nothing. So you can say that this is a very sharp function, sharp peak, and then almost there is nothing. So that's why we are saying that this is this particular region is defining the width of the this function, cardinal sine function. And if it is so, then I can write down this difference in energy, the energy difference between the initial and final state, as E delta E m n, which is nothing but is going to be 2 pi h cut by T1. So what it suggests? It suggests that transition to the final state m, it suggests that transition to the final state m, for which delta E mn, the difference between these energy states, this energy and this energy, two state energy difference does not deviate from 0 by more than 2 pi T1 by 2 pi h cut by T1, this value. If it is deviating than this value, then this function will become 0, this cardinal sign function becomes 0, and that is why population becomes 0. So, what it suggests that I can have an population transfer from end state, initial state to the final state only if this final state energy has to be within this width, plus minus width. So, if this is the energy of EM, then both side is possible, this side and also this side is also possible, this side. So, I have I will draw it like this way. Let us say this is the allowed energy states. So, I cannot go beyond this energy spacing. So, population transfer can only possible from initial state to the final state if the final state energy stays within this EM minus delta EM or plus EM plus delta E Mn within this state, where we are assuming that En equals Em. So, all these possible states can be populated with a varying population, but it can be populated. But if the states are here or states are here, it cannot be populated because it is going beyond the allowed energy spacing, which will be controlled by this cardinal sign function for this population in the final state. So, bottom line, what we have learned from this exercise is that transfer of population, non-radiative transfer of population from initial state to the final state is possible only when if the final state energy difference, this is the delta E, does not deviate from 0 by more than this value. This is going to be plus minus. Both values are possible. So, all those states will be populated if they are within this energy bandwidth. So, what we have noticed that the transition from initial state N may occur towards all possible final states whose energy Em is located in the energy bandwidth of this. So, I have this N state, and then I may have many other states here as a final states, but only those states which are within this bandwidth. So, this is if it is En energy, then the same energy would be Em, and then I will have this is minus delta E Mn, and this is plus delta E Mn. They have to be within this bandwidth. But it may so happen, I mean this is all allowed according to this equation. All possible allowed transitions under this non-radiative process is this. But if I have a situation where I really do not have this many states even within the bandwidth, so I do not have all the states, let us say, I have only one state. If I have one state available within the allowed bandwidth, then what will happen? it is going to be then state to state transition. So, I will have a state to state transition, because I do not have many final states. And within this state to state transition, if this state to state transition is going on, then one can say that I can take one particular limit. This is a mathematical limit we are taking. T1 tends to, let us say, infinity. What does it mean? It means that I am allowing the system to be to interact for a long time. So, it means that I am using the long time limit. T1 is the interaction time, 0 to T1 is the interaction time. So, we are allowing the system to interact for a long time, and if it is long time, then one can write down this cardinal sine function, square omega mn T1 divided by 2 limit of T1 tends to infinity. Within this limit, this cardinal sine function becomes a delta function, and it can be written as 2 pi T1 delta omega mn. So, this is a definition of a delta function. I had a very sharp, so basic idea is that this function is a very sharp function, this cardinal sine function, and at that infinite t limit, which means very long T1, if T1 is very long, then what happens, this sharply peaked function, cardinal sine function, adopts the Dirac delta function in the limit that the peak height of the sharply peaked function becomes infinite. So, this becomes like this with 0 width, is a delta function in the limit of this t tends to infinity, which means the area under the curve will go 0, because it's now for the long time, and it becoming, the height would be infinite, and it behaves like a delta function, omega mn delta function. So, within this limit, within this long time limit, this entire population in the mth state can be written as follows. One can write down as follows. This is going to be then h mn dash square divided by h cut square. Then I have 2 pi T1 delta omega mn within this limit. So, this function is becoming a delta function for a long time limit, and there is a property of delta function which is delta Ax is nothing but delta x by A. So, because omega mn is nothing but Em minus En divided by h cut, we will be able to write down this as follows. This is going to be then 2 pi by h mn dash whole square divided by h cut square, then 2 pi, then T1, and then I have this T1, then delta, I have this h cut also, and then delta Em minus En, what I get here. So, rate of transition, so this is the population at the mth state. Okay, this is the population at the mth state, and the rate of transition, if we try to find out the rate of transition, that is going to be P mn divided by T1. That is nothing but this equation. So, what we get here is that presence of a delta function in this equation, this delta function in this equation, it means that this function will have a finite value, finite positive value whenever you have Em equals En. If they are not equal, then this entire value becomes 0. So, presence of a delta function in this equation mandates the fact that in the limit t tends to infinity, which is the long time limit, only transition which will be allowed is the one for which the initial and final state must be equal. So, this must be equal, otherwise the transition will not be allowed, because delta function will be 0 for every other state. This requirement is serendipitously fulfilled by certain electronically excited states of helium and neon in Heine laser. So, in Heine laser we have seen that this helium excited state and neon excited state, they are coinciding with each other. They should have the same energy, and then only this helium can transfer energy. It can de-excite, and the entire energy can be given to excite a neon ground state system to the excited state system. This equation is called Fermi's golden rule of state to state non-radiative transition, where we have this involvement of the delta function. We will now move forward to the state to continuum non-radiative transition. In the state to continuum non-radiative transition, our starting point again, this population in the mth state, which is defined by this cardinal sine function square function. This is a very sharp function, and the concept again has been depicted here. As you can see that this state can transfer population to the to a number of states, possibly number of states if they are available, but within the band, within the energy bandwidth. So, this is the definition of the bandwidth we have given. This bandwidth is delta E. Within this bandwidth, plus minus delta, so this is plus delta E, and this part is minus delta E. That is given by this eta plus minus eta. So several final states are available. If they are available, then the allowed bandwidth, the bandwidth of this transition, which is controlled by this cardinal sine function, will allow the transition to happen from discrete initial state to the number of final states. And if the final states are so closely spaced in energy, they can form the continuum. They may look like a continuum. And if it is continuum, if we are dealing with continuum, then we have to make use of a quantity called density of states, because we do not have one state, we have multiple states, and when you have many states together very closely spaced together, then often we use this quantity called density of states. Density of states rho em. At a particular energy level, it is defined by number of states present per unit energy range between Em and Em plus d Em. So within this range, within this interval, per unit range, how many states I have, that is called density of states. So in that case, this rho Em DEM will represent number of states present in the DM range. And we have already realized that, so this is the number of states present in this range, DEM range. And for each state, the probability of transition is given by Pmn, that is given by, we have seen that Hmn dash square divided by h cut square T1 square cardinal sine function square, then Em minus En T1 divided by 2 h cut. This is the probability of transition to each state, and we have this many states. That's why total transition probability would be, for transferring the population to this many states, will have rho Em multiplied by rho Em dEm. So this is the total probability of transition from to this many states. And if we say that the radiationless transition occurs from an initial state to a group of final states whose energy Em lies within an energy interval from Em plus eta to Em minus eta, in that case the total probability will be given by this integration. Integration is going to be Em minus eta to Em plus eta h Mn dash square divided by h cut square, then T1 square, then cardinal sine function square, Em minus En, then T1 divided by 2 h cut, then rho Em dEm. So we are integrating the contribution coming entirely from this region, this energy space. All the contributions we are calculating. So each state probability of transition is given by this part, only this part. Then we are multiplying by this, because this is the number of states I have within this energy range, and in the end I am just integrating the total contribution. So if we do that, then what will happen here, we can assume that for each state, so I had an n state here and it is transferring the population within this entire interval, within this entire interval I am transferring the population. When I am transferring the population, we will assume that for each state transition, I will consider that the density of states, this rho m, is constant to make the mathematical derivation simple. Density of states will be constant, and we will say that h dash mn, this coupling term, is also constant. So, for each state, final state, density of states is constant and coupling constant, and that is why if it is constant, then we can take them out of the integration, and if we do that, then finally this integration becomes P mn total, it is going to be h mn dash by h cut square, then rho em, then T1, then this integration em minus eta to em plus eta, then cardinal sine function square, em minus en T1 divided by 2 h cut dem. So, just an integration between these two. And we have already understood that non-radiative transition may occur from an initial state n to those final states whose energy Em is located within this energy bandwidth. That is exactly what we have already understood. So, one way to further reduce this equation is to assume that eta is actually greater than 2 pi h cut by T1. What does it mean? It means that the number of available states, it is showing that the number of available states, so eta is controlling how many states I am going to integrate, and this part is controlling how many states I have available. So, this condition suggests that the available number of states are significantly greater than the required final states within this energy bandwidth. So, this bandwidth, which is plus minus this value, this delta E value, this is given by 2 pi h cut by T1. So, what we are saying is that number of states here as depicted here, number of states are much larger than the required bandwidth for this transition, and if this is so, then one can assume that this integration can be considered to be from minus infinity to plus infinity within this limit. So, if I have states which are available states is much larger than the states where I can transfer the population. If it is so, then I can transform this integration within the limit of minus infinity to plus infinity, because if we do that, then very easily we can calculate this integration. It is because I can assume that Em minus En T1 divided by 2 h cut is nothing but x, and in that case I can write down Dem equals 2 h cut by T1 dx. I can plug that in here and I will be able to reduce it in a following way. I can use the standard integral for the cardinal sine function is follows: minus infinity to plus infinity, cardinal sine function x dx is nothing but pi. So, we will use this standard integral, and if we do that, then total probability, I will find out total probability Pmn total is that Hmn dash square divided by H cut square rho Em T1 square 2 H cut by T1 pi. So we get this T1 will be cancelling each other. So I get this H cut will be cancelling each other. So I get finally this is what we get as the total probability of transition to all the allowed states for this transition, and as a result the rate of transition will be given by this equation. So what we see here is that this equation is quite similar to state transition, except for the fact that here I have density of states, and there I had for the state to state transition I had this delta function. But we remind here is that this rule, Fermi's golden rule for the state to continuum transition, the derivation has been done under the assumption that I have available states much larger than where I can transfer the population. So within this limit, I'll be able to get this. So there are two rules we have found already, and these two rules are suggesting that the transition rate will depend on density of states and the coupling strength. If the coupling strength is strong, then transition rate would be high, and if the coupling strength is weak, then transition rate will be low. How fast the energy population can be transferred from the initial state to the final state. We will stop here, and we will continue the session in the next class.